just I almost never get sick. I haven't been sick. I can count on like one hand the number of times I've been sick since my kids were born. But
You did get like a doozy of an illness a couple of years
I know
ago.
it was some people complained in Astronomy Cast. We're live, by the way. People complained in Astronomy Cast because my head cold sounded so bad. It was the worst. So yeah, but no, I'm still getting better. But I'm gonna go back to bed as soon as this show's over, and take a bunch more ibuprofen. Yeah, yeah. Hey everybody. But I'm definitely I'm 74% recovered now, and seeing how my wife's timeline is and her daughter is, I know sort of where I am. Like I got my hearing back today. That was nice.
Yes.
And also I'm refusing to see anybody else. This disease stops with me. It stops right here. It doesn't make any more entry into Canada. That is it.
You are doing the right thing.
Yeah, I'm washing my hands nonstop. I'm turning all of my friends away until we're done. Sending the children out into the Arctic, and so that they don't get sick. Hey everyone, welcome to a episode of Astronomy Cast. Did your dog just close the door?
Yes. I love how you're now a dog owner, so you recognize these noises.
Yeah. The arbitrary, non-stop attention of a dog.
Yeah.
I'm gonna say hi to a bunch of people. Hello to Arnold Post, Astro B, Barrett Kleinkar, Chris Adams, Daniel McCool, Duck Sandwich, Ilad Avron, Guido Bibra, Harry M, Helg Bierkog, JL Fox, John Siffel, John Victor, Johnny Zed, Michael Jobin, or Jobin.
How many Johns did you just name?
I named 3.
Many.
No, just 3.
Okay.
Michael McLaughlin, Mike Dennison. I just did 3 mics. Paul Gracie, Peter Quinn, R. Instro, Renan C. Brazil, Rick Schwartz, Ryan Schmitz, Sylvan Westby, Susie, our producer Murph, Tom Nathy, and Yoav Landsman, who I got to have a really great conversation with at our live event, which I am wearing the shirt for, by the way, at our
Excellent.
at our event in
Louis.
St. Louis. I got to sit down with Yoav and find out how I could build my own satellite, and he was really helpful and gave me all of the answers, and it was wonderful. So, and there is no recording of it, I don't think. Did we? I don't think we. No,
really?
it doesn't exist. It's gone forever.
Oh, God.
Yep.
Okay.
It's fine. Sometimes these things just have to go away, like tears in the rain.
Okay.
Duck Sandwich. I've talked about Fraser was washing his hands a lot. That can't get clean. Never get clean. What? Jessica Felt says, "Hey Fraser, hey Pamela." Oh, is it too late? You got to remember how this works is that you have to go and say hello in the chat, and then I can say your name. If you don't say your name in the chat, then I won't say hello. I'm sorry, but that's how this works. I am ready to begin a live episode of Astronomy Cast.
I think I am too.
Yay! Then
Checking. Hold on. Audacity's using the wrong mic. Stop that, Audacity. Okay, Audacity is now using the correct mic. I am ready to record. Are you ready to
I'm ready to press record. I'm going to press record. Here it comes. Here it go.
I've pressed record.
All right, I've also pressed record. Let us begin. Astronomy Cast, episode 458, The Science of Cassini. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Cain. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, the Director of Technology and Citizen Science at the Astronomical Society of the Pacific, and the Director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing, Fraser?
A little sick. So people are going to hear that in my voice. I got a bit of a cold.
And we're both going to provide Chad challenges by sniffling into our microphones.
And coughing, yeah.
Yeah, we're sorry, Chad. We do love you.
Yeah, so just give it a listen, Chad, and make sure you cut out all that sniffling and coughing. So I've got one little bit of self-promotional thing to do here, which is that not only has Astronomy Cast returned, but the Weekly Space Hangout has returned to grace your earballs. And we are doing the show at a different time live, but we're also putting a lot more emphasis on the actual podcast version of the show. Morgan, Kimberly, Paul, all doctors of their respective fields, are now permanent co-hosts of the show. We've still got special guests. It's a really good time. So if you want to hear the sort of the news portion of the space, then make sure that you do a search for the Weekly Space Hangout. Join us live. We do it at 5 o'clock on Wednesdays now. But also the podcast is well worth listening to. So check that out.
And that's 5 o'clock Pacific time zone on Wednesday, 8 o'clock Eastern.
That's right. And have you got anything self-promotional that people should be aware of?
Not today, but the other thing that you need to promote, which actually goes along with this show, is you worked with David Joseph Wesley to do a piece commemorating Cassini that is truly beautiful. And can you share its URL with our audience?
I can, but I mean, it's going to be like a YouTube dot blah, 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 you know what I mean? So,
okay, fine.
Yeah, but you're exactly right. So David Joseph Wesley, friend of the show, and composer for Hollywood. He does movie trailers and video games, and he let me know that he was composing an album just for Cassini. And I said, that's awesome. Why don't we edit a video together to go along with some of your music? And so we made a deal at the event in St. Louis and then put it live. And we actually posted it the seconds after we had after we got the last images from Cassini. And actually, Chad did all the editing work. We made things a little different. I wrote all the text, but we put it as closed captioning, so you can actually turn it off and just listen to the music and watch the video. And if you want some of the underlying explainers and science, then you can turn on the closed captioning. So it's on my YouTube channel, and fairly recent. It's called Farewell Cassini, the Grand Finale, and the Final Images of Saturn. Check that out. It was a lot of fun, and David did an amazing job.
And I just love working with artists who can give us such a different insight into our science. So everyone go play with your brains in a different axis.
Yep. And now Cassini's gone, smashed up in the atmosphere of Saturn, but planetary scientists are going to be picking through all those pictures and data for decades. Let's look back at some of the science gathered up by Cassini so far and what we could still learn from this epic journey. Where should we start? So I think the point of this episode is to just kind of look back and refresh. You're all feeling sad about the loss of Cassini, but let's just remind you of all of the big scientific discoveries that were made over the course of the mission, and some of the things that are even just works in progress that we can continue to understand. So do you want to start from a timeline standpoint and just kind of go back to the beginning? Because, I mean, Cassini was doing science even before it got to Saturn.
Yeah, that's entirely true. And they didn't just do science of Saturn. I mean, they did that, of course, but they also captured images here at Earth on a flyby. They captured images of Jupiter with this somewhat iconic photo of Io transiting across Jupiter on January 1, 2001. So we have this mission that has studied everything from asteroid 2685 Mazeroski through to the most detailed facets of the rings of Saturn.
And I mean, with Cassini, they actually didn't pass super close to Jupiter, so it wasn't able to take those same level of quality images that it took when it did the Saturnian system. But still, it was sort of one of the most powerful spacecraft and most well-equipped to pass through the Jovian system on its way to Saturn. So did it contribute some of the science about Jupiter?
Well, one of the things that it really did was it gave us that full world view that you don't always get when you're orbiting up close. So if you think about it, if you're orbiting close to Jupiter, it's going to fill up your entire field of view, and there's no rational, non-fisheye camera that's going to let you capture all of this at once. So by flying at a fairly good distance, they were able to get the big picture. And with Jupiter, the big picture means you can study ring dynamics, you can study the atmosphere, and they were able to start to get really neat insights into how that atmosphere is circulating, what is causing this alteration between the dark belts. These are the ruddy colored ones that are either orange or dark flesh toned, depending on how you want to look at them, and what filters you use, and those white or ivory colored bands. So we studied the belts because we could, and we had a full world view back in 2000.
And I think some of my favorite images of Jupiter come from Cassini, especially, as you said, those images of some of the moons. It got this great image of Io just transiting right in front of Jupiter. And I mean, I think at this point now we're up to 450,000 images came back from Cassini. 450, I forget the exact number, but it's enormous. Came back from Cassini. 25,000 of them were taken in the Jupiter system. Like, it just took an enormous number of pictures as it made that flyby. But this is just the beginning. So let's talk about actually some of the science that it did as it made its way into the Saturnian system.
So one of the things it did that we don't pay enough attention to is it studied not just Saturn itself, but it also studied gravity and the general theory of relativity. So here we have the mission and its lead up getting to Saturn. It's looking forward, it's looking for deviations like the ones that we saw with Viking and Voyager. It's looking for the curvature of space. And while it didn't help us figure out what is up with the Voyager time anomalies, which we've done entire episodes to, they did show, once again, relativity is right. So just add one more notch to relativity. And that really starts to get at the end of the non-Saturn science. So we have an asteroid, we have the moon, we have Jupiter's moons, general relativity, and then all things Saturn. All things Saturn.
All things Saturn. And I really remember as Cassini was coming into the system, and we got that first look at its first moon. Was it Phoebe? I'm trying to remember which was that first moon that it saw.
Phoebe.
It was Phoebe. And it was and I know Voyager had never gotten that close to Phoebe. So it was amazing what those first images were. It was so much better than anything we'd ever seen before.
And this isn't a big moon. This is a little tiny beat up potato of a moon. And it's not a beat up potato like an asteroid is. It's instead made up of ice as well as rock. And so you have these places on the surface that are pure white where they've recently been revealed. And this was when we first started to realize, well, I mean, we suspected, but it was when we were first starting to get really clear evidence that some of these moons are essentially the stuff of comets, but orbiting as moons.
Right. And so you really got this evidence that Phoebe was this captured comet or asteroid, comrasteroid.
Well, and this is where we start to get down to, we're realizing more and more every year that there is a continuum between completely rocky objects and completely icy objects. And I'm not sure we found an extreme of either yet, because the harder we look at the earthy things, the more volatiles we find. And, well, we keep looking at icy things that have gravel. So with Phoebe, what we found is a large amount of water ice that is part of an asteroidy moon. So yeah, comet asteroid.
And then of course, all of the, we mentioned at the beginning of the show that we did this video, and so all of this sort of these timelines, milestones are sort of kind of fresh in my brain. Is that then, as it sort of came into the system, the Huygens probe, which was this European probe, detached, and it was ready to do its mission to get to Titan. Now, do you want to talk about the flyby-sides of Titan, or do you want to talk about the science done from Huygens first?
Well, it all sort of tells one interleaved story. So you have the summer of 2004 is when we get that first amazing flyby of Titan. There was surface imagery, there was radar imagery, and this was when we were starting to see, oh, wow, there are lakes of methane that appear because of the difference in gravity and the difference in temperature to geologically act very similar to water lakes here on Earth. So we've said it before, we'll say it again. Water here on Earth is at that magical triple point where various points, various times, you can have water vapor, you can have icy water, you can have liquid water. With Titan, you have liquid methane, gaseous methane, clouds, fog, and then you have methane ice. And this triple point cuts away at the low gravity surface, and you end up with, well, as they found that summer, lakes of methane. And 6 months later or so, when in January of 2005, Huygens descended through those orange thick clouds, it was off to see just how much it could image before, well, all the things that naturally demise a spacecraft took over.
So let's talk about that. There's a great animation. One of the most powerful images from that mission was this great animation that the folks from ESA did, showing Huygens going through the cloud tops and being able to come down to the surface of Titan. You could see kind of the mountains and the landscape as it got closer and closer and closer, and then like pebbles on the surface as it landed, with a thump on the Titan surface, and not a splash into the methane ocean, which it was prepared to do. And then it gave us like 70 minutes of science before its batteries ran out.
And what really got me was this is clearly some sort of a river delta region. And if any of you out there fly a lot, you know that when you look down over a landscape that either has rivers cutting through it or has had rivers cutting through it, you end up with these thick channels and then all the tributaries coming off of that. And the reality is the tributaries are feeding into that main waterway. And we see the exact same tributaries and main waterways when we look down at the features that Huygens saw. And coming in for a landing, it's this amazing landscape where you have to remember what scale size you're dealing with, because it just looks like this boulder field stretching off into the distance until you look and realize, oh, those boulders are just 10 to 15 centimeters across. So this photo is basically the same thing as setting your camera down on the slightly rocky shore of a river and catching all of those rounded river stones in your photo. And these are rounded river stones.
Yeah. And I think this was one of the big goals of the whole mission really was that they didn't know, because the Voyager wasn't equipped to be able to see, didn't have that ground penetrating radar, wasn't able to see through that haze, that hydrocarbon haze on Titan. There was no idea what was below this surface. There was just, it's kind of yellowy brown, thick atmosphere. That's all we know. Maybe there's some kind of hydro system going on there. Maybe not. We don't know. And Cassini went with the right tools to be able to see, both to land on the surface and to be able to see the whole world from above.
And what's cool about having such a thick atmosphere and such a low gravity field is Huygens didn't exactly drop like a rock. It rather kind of It didn't float and flit, but it did descend nice and gradually, giving us more than 2.5 hours of transit time down to the surface, transmitting the entire time.
Yeah. It's that, and then I mean we can come back around later a bit, but I mean, we learned because Cassini was able to make so many flybys and orbits of Titan, each time kind of getting closer and closer and closer, it was able to make all of these amazing findings about this system, about these methane seas on Titan. So can you go into some of the kinds of science that was returned by Cassini?
So there was roughly 50 flybys of Titan over the course of Cassini's many years out at Saturn. And it was able to discover seasonal variations. One of my favorite discoveries of all is they saw these storms billowing up as the seasons changed on Titan, as the spacecraft went from its equinox mission over to its solstice mission. And with this change in seasons and this arising of storms, they saw the surface in various parts go from being all shiny as though it had been snowed upon to being normal, which kind of means it snowed and then sublimated. And that is awesome. And in other places, it got shiny and then dark, just like it snowed and melted. And it's really awesome to be able to look at another world and see changes in surface color that appear to correspond to the same sorts of phenomena that we see here on Earth. The storms being seasonal, that completely makes sense, but we saw it, and we just like to see these kinds of things. And we're still baffled by the chemistry of Titan. The chemicals don't seem to be in the kinds of equilibriums we expected. The lakes don't have the ratio of methane to ethane that we expected. It's forcing us to rethink chemistry and try and figure out what's going on and dream of days that we can sterilize a spacecraft enough to justify sending it down and doing long-term explorations to try and understand what's going on this little world.
One question that was brought up, and this is, me completely rabbit holing, which is that, the death of Cassini was done because they didn't want to have the space. We talked about this last week. They didn't want the spacecraft to crash into one of the icy moons and potentially pollute it with life, Earth life. And yet Huygens went to the surface of Titan and sat there, and, it's possible that there's a whole other level of subsurface ocean that is an icy ocean like you have on Enceladus on Titan. And that's a bit of a, why'd that happen? Why?
Well, and who knows what sort of methanogens or ethanogens, I don't know if that's a thing, could exist in Titan's lakes. This basically comes down to, we send a spacecraft and we realized, expletive, it might be capable of sustaining life out there.
Right.
Mistakes. I don't know if it was mistakes. We learned something, and we didn't have a robot that roved. It's the rovers that are more problematic. So yes, there's potentially one place where there's little trilobites going, or tardigrades rather. There's little tardigrades going, I'm here in my chrysalis, waiting for the opportunity to emerge. Hopefully there aren't little methanogens native to Titan going, oh God, we're dying.
Right. As the tardigrades plant their little flags in the Titan, methane sands. So let's go on to Enceladus then, which is sort of one of the next. And again, many flybys of Enceladus and bits and pieces figured out over time. So let's have some of the highlights of what was found at Enceladus.
Well, it's hard to know where to start other than that sucker's got water. And each time they went by, once they realized there were ice geysers, more and more was looked for, and more because we looked was discovered. This is the awesome thing about having these multiple attempts at going by, is you can do refined science. So you start with, oh, wow, geyser. Okay, go back, try and get sample of geyser with the dust capturing instrument. Try and measure differences between the internal rotation and the surface rotation. Try and get all of these measurements that in different ways build up a picture of what is the ocean, what is it made of, and how extensive is it. And through combining passage after passage and all the different instruments that Cassini had to offer, we were able to build up this model where it appears that Enceladus has extraordinarily salty seas that allow the surface to not be coupled to the rocky core, which implies that the oceans are expansive, allowing the surface to essentially float on top of the ocean. And it's largely because of Enceladus that we had to kill Cassini, deorbit Cassini violently. And one of my favorite things about the mission, and I don't even know if this was part of the intention, and I really want to find someone to ask, is one of the last photos to come back was of Enceladus, basically setting behind Saturn.
I haven't seen. I'm gonna see if I can dig up that image while we're going through the show. But
so here's this picture of Enceladus setting. That's one of the last things to be seen by Cassini, that burned up, that whatever life may exist on Enceladus can continue to exist and not accidentally get killed by Cassini. So it's just this terrible poetry of, I'm dying for you and I stare at you as I plunge into the surface. And I don't think that was what was intended, but that's where the worked on the high school literary magazine part of my brain went.
We can kind of fast forward to some of the most recent observations, which was this stunning discovery that not only does it have these geysers, but in fact there are these hydrogen molecules or
hydrocarbons.
No, but hydrogen, like food for
yes.
Food for methanogens or for various extremophiles is actually percolating around. It's probably being released from vents at the bottom of the ocean and is making its way out into space, where Cassini was able to sample it, which is the most exciting discovery for astrobiology in the solar system.
And it's just one of so many worlds where we know that Europa has even a greater volume. So when you start realizing this is just the first one we've looked at in detail, what else do we have to discover when we start going through the geysers that are associated with the hot spot on Europa with the next mission we send that direction? This is just a tantalizing start to understanding these icy worlds.
Yeah, more spacecraft necessary. Let's move on. So do you know what my favorite moon is? Do you remember?
I think it's Iapetus.
It is Iapetus, yeah. And I love the way Iapetus looks. That has this, this dark side and this light side, and it has this ridge that just looks like it's straight out of some kind of science fiction movie.
And it has these dark splotches along the boundary between the light side and the dark side. And the splotches, they're so black that they kind of look like, and the great nothing ate this part of the moon. And it's this fabulous case of light and dark have different thermodynamics. So as this little moon goes round and round Saturn, one of its sides happens to be picking up all of the organic darkness, dark, smudge, sooty, complex organics. And I don't mean sooty as in terms of burning, but I mean it in terms of like the structure of the molecules. And that material builds up on one side of Iapetus. It heats up a little bit more than the light side does. So the volatiles evaporate away, go, and then settle down and re-brighten the white side where it can happily freeze back. So you have this volatile cycle going on. And it's just super cool. And this equatorial ridge, that one is more mysterious. We think maybe it's just because it's where it tends to accumulate stuff and things, but that model doesn't totally work. It's weird.
It's where it ate a ring.
Yes.
Maybe.
Yes.
Right.
We don't fully know.
It's
awesome.
More research necessary. Time to send another mission back. But again, these are just a couple of them. We've got, Iapetus, my favorite. You've got Rhea and Dione and Hyperion, which looks like a sponge cake.
Yes, and then you have the ravioli, otherwise known as Pan.
Yeah, is that your favorite? I don't know.
It's the most endearing. I don't really have a favorite of Saturn's moons because, like, part of me is like, Titan, it's so cool. The chemistry doesn't make any sense, and chemistry doesn't make any sense anyways. Then there's like Hyperion, and then Mimas, of course, looks like the Death Star. So who doesn't love Mimas? But Pan looks like a ravioli, and we always record after lunch that I have skipped prepping for the show, so it always comes up.
Right, and where you come from is known for its fried ravioli.
It's true.
Yeah,
it is true.
I discovered that. There's a couple of things that I thought were pretty great with Saturn as well. One is, like, on the planet itself, in the mid part of the mission, because, as we said earlier, it got a chance to see the seasons move through the planet. It got to see this amazing storm appear in the northern hemisphere in sort of 2010-ish, 2012, sort of, halfway-ish through the mission.
And this is one of the great things about how the mission kept getting extended is first it saw this fabulous moment of the sun being edge on to the rings around equinox. And then as we came out of equinox, heading towards solstice, past 2009 was like the most boring year to ever look at Saturn. Heading into 2010 and beyond, as the seasons changed, there was this storm that was first noticed by amateur astronomers because you can see the full disk, and it slowly spread across the mid-northern latitudes and just spun up, creating a white belt of storm. And that was just awesome. And it showed that you have this rich, complex chemistry, you have thermodynamics at play, you have all of these different materials that when they change what ratio is where in the atmosphere, you get changes in color that go with the storms.
I'm going to apologize. I'm like looking through. So Cassini, for the Cassini mission, NASA put together this, for the grand finale. Every year they would put together these sort of top 10 science discoveries. And it's like choking on a fire hose. I mean, like, this discovery of an ocean of water on Titan, as I mentioned earlier, underneath that methane crust, underneath the ice crust, like this, the discovery of, even on Titan, this southern polar vortex that changes with the seasons, the source of the rings, which were, like where some of its rings came from, thanks to some of the moons. There's just too much.
The hexagon that changed colors.
Yes.
So there's this crazy, I think we did an episode on it, or at least we talked about it extensively earlier. And then there's certain things that Cassini was supposed to figure out and couldn't. Like how long a day is on Saturn. We do not know this precisely.
Still don't know that.
No, it's because the radio source that we used with Voyager apparently moved in altitude, or Saturn changed its day length by 6 hours, and that didn't happen. So yeah, Saturn is awesome and confusing, and now doesn't have an orbiter. And one of the things we haven't brought up yet is Cassini was built on a legacy of the Mariner missions, of the Voyager missions, where this was tried and true and proven hardware that had been used for explorer after explorer after explorer. And it's the last of that line. And we don't have any great explorers built on this same hardware platform that's so tried and true and awesome, planned for the future. And we don't really have a lot planned for the future. So we're glad we have so many gigabytes of data, because we don't know we're going to get any again.
Yeah. And I think sort of, as its final project is, we talked a bit about sort of the death of it and how that was coming together. Earlier this year, back in, was it April, they changed its trajectory to do something very risky, that it was going to pass in between the planet and its ring system, taking images as it went of both the planet at a closer level than it had ever seen before, but also the rings from a perspective that it had never seen before, passing above and below and above and below. And that science, I'm sure we haven't heard the last of that part of it yet, that as its final act, it gathered all of that amazing, all of those data of the rings, and we're going to see that coming out over the next, planetary society meetings and planetary space meetings over the next decades, right?
And part of it is we still are working to build powerful enough computers to fully understand the dynamics of the rings and the density of the material. And we're just getting to the point that we understand that, just like the density of water in the atmosphere and the opacity of the atmosphere don't always have a one-to-one correlation. You can look through a rainstorm easier than you look through fog, even though the fog isn't as dense as the rain in terms of like particles of water per square meter. We're finding that the rings of Saturn, the places they're most opaque, aren't the places where they have the highest particle density or density of material per square meter. And having that kind of information changes how we do our models. We're starting to have better and better understanding of where are all of the gazillion moons. They still haven't even named all of the ones that Cassini found. There's one lone little moon that still has a license plate instead of a name. And as we understand the origins of the rings, as we understand the shepherding moons of the rings, as we understand the densities, as we understand how gravity waves propagate through them, how you get these spoke structures, well, the how we get to the as we understand part is as we build bigger and better computers that can run more sophisticated computer models, we'll eventually get the theory to match the data. But we've got the data.
Yeah, we do. And all of those images, all of those data, right? Like it's just an enormous amount of material that is back. One thing that I really love when people are like, where are all the real pictures from Cassini? I can point people at the reverse dated raw archive of 450,000 pictures of Cassini that you can just take, download, process, do what you want. Go ahead. All that data, it's all there.
And a shout out to the unmanned spaceflight community, because they have people that have figured out how to do amazing, masterful processing. And in the final days of Cassini, while the science team and the imaging team were all up to their eyeballs in making sure they were getting every last ounce of information out of all of the storage units and memory and downloaded to Earth, while they were working on the spacecraft, it was these folks that were sending out the last and final pictures in their full color glory to allow us to see one last time through Cassini's, well, not eyes, but through its cameras.
Yeah, absolutely. All right. Well, thanks, Pamela, and thanks, Cassini. We'll see one of you next week.
I'm hoping it's me.
I'm sure it's you.
Okay. Just checking.
All right. See you later.
Bye-bye. And now we save. Trying to record an episode when my nose is clogged and I have to breathe through my mouth is much harder.
4:58, just in case you
Thank
were
you.
wondering. Just give us
And
one
you did not
second.
have a single coughing fit, so you're...
I'm holding it back. When I shut this down, I'm going to then cough up a lung.
Okay. Just so long as you, like, reinsert it afterwards.
Yeah. Ugh, that's gross. It is helpful having a respiratory therapist as a wife.
Oh, yeah, that's
Yeah.
super helpful.
Yeah, it really is. So I'm thinking now. I don't know if you've heard, and I know you're not able to comment on this, but I can. That the potential new administrator for NASA is thinking that it might be a good idea to search for climate change on Mars. And I think that's a great idea. I think because to search for climate change on Mars, you're going to have to send some kind of, like, I think the best way is like ice cores from the Martian polar cap. And so you could send some like really amazing mission to Mars to land, possibly with astronauts, to then do deep core analysis on the ice caps to check temperature levels, gas distribution, things like that, to find out. And you know where else would be, you want multiple samples across the solar system. So the other place you should probably go is Enceladus and Europa. You should send separate landers, potentially astronaut missions to both Europa and Enceladus, perform ice core analysis on those worlds, and analyze what's inside those ice cores to search across the solar system. I think that would be really, that would be a very useful next step.
So I actually asked about what it would take to do ice cores on Mars. I think I asked Kevin Grazier. I may have asked somebody else. I know I asked a real planetary scientist because, remember, I'm an astrophysicist. I asked a planetary scientist about this. And the issue is the weight of the thing required to go and drill that deep. And we don't have a spacecraft yet to do that.
Okay, so we're going to need...
So
that's fine, right? Someone's going to need to develop a heavy land capability spacecraft that can travel to Mars. You're probably going to want, as I said, you're going to want astronauts. You're going to want astronauts capable of running equipment that complicated to run ice cores that big, that long. Think about the complexity of pulling ice cores out of Lake Vostok, right? Like it's hard work. So you're going to want...
And we need scientists to do the analysis. Just don't forget the scientists to do the analysis.
Yeah, of course. Who else would you have do climate change analysis than climate scientists, right?
Just making sure you add it to your list.
It's on my list. So just to be clear,
okay,
right? To follow in this, we're going to need to send we're going to have to finish the development of a super heavy lift vehicle. We're going to need a method for landing very large payloads on the surface of Mars, probably including human payloads, because they're going to have to do the work in some of the local analysis of this material, as well as a lander on Europa and a lander on Enceladus, and to be able to do this research. And I think that if you're going to bring those samples back, you don't need to have those samples like right now. You're gonna have to sterilize the samples.
Don't bring them back.
No,
Do not bring them back.
Right. So take them to a new, probably rotating space station at the L1 Earth Moon Lagrange point.
No, just leave them on Mars and send the humans.
No.
And
I
the
think
equipment.
you're gonna but you're gonna need to bring the humans back and some of the samples back. But you're not gonna bring them to Earth. You're gonna bring them.
But you're not gonna bring back the whole ice core.
Yeah, you are. You're going to bring it to this huge rotating space station system complex. It's going to need to be built at the L1 Lagrange point.
You haven't watched Andromeda Strain.
Don't bring it to Earth. Bring it to the new space station that is going to need to be developed at the L1 Lagrange point. That's all I'm saying. To study it.
You didn't read the Expanse book series. You need to read the rest of the series.
So I'm offering to hollow out an asteroid, set it spinning, return it to the Earth 1 Lagrange point. You don't want this?
I want all of that except for the ice core that may or may not have life forms that would kill all of humanity trapped in them.
They wouldn't. Anyway, they're never going to get back to Earth because they're going to be in space at the new, let's call it the Pamela Gay Science Space Station. Let's call it we'll call it the Pamela Gay, the Dr. Pamela Gay Astrobiology Research Station. Okay?
And that way my name is remembered forever. When everyone dies.
When everyone dies. No one's gonna die. Everyone's gonna appreciate the deep and meaningful science, and we will finally get an answer to that climate change question. Is what I'm saying. Then we will know, if it's happening here on Earth and if it's happening across the solar system. That's what it's going to take. That's what I want to hear. That's what I want. That's what I need to see. All right. That's what I think. Let's hear your questions for Dr. Pamela Gay. Let's see. I saw a question earlier.
Daniel McCool agrees with me. Just saying.
Fine. That's fine. We what matters is the total amount of evidence that is delivered. Come on, someone here with a question then. Okay, ML Robinson wants to know, is Titan in some way an analogy for the early Earth when methane was more prevalent?
Probably not, because the temperature structure is so different.
Right. It's cold there. You don't need a spacesuit. You just need a really, really warm jacket.
Radiation. You need a radiation suit. It's very warm and oxygenated.
So here we go. What was the name? Someone had a good name for the Dr. Pamela Gay Astrobiology
Center for Research and the Apocalypse.
And the Apocalypse. There you go. Yeah. The Pamela Gay Center for Research and the Apocalypse. Perfect. Yeah.
So, can you mention the Osiris-Rex Slingshot? Yes, we can, James Aberson.
We sure can.
So earlier today, I think 5 or 6 hours ago now, I've lost track of time, the Osiris-Rex mission got closer to the Earth than it has been in the past more than a year, because it used to be on our surface. Then we launched it a little over a year ago, and then it came back. And it got closer to the Earth than the geostationary satellites, stole some of our energy, essentially, as a planet, and used that energy to accelerate itself further out so that it is now on its way towards Bennu, where it will go and find a rock to pick up. And we are going to get the help of all of you to find the rock using the CosmoQuest virtual research facility.
Which rock is coming home?
Yes, you guys get to help us pick the rock. So go check that out. And hey, go map other worlds. You can do that today.
And wouldn't it be better if this rock went to the Dr. Pamela Gay Astrobiology Research Station and for the apocalypse?
You're going to get me in so much trouble.
I'm just saying. Tom Nathy thinks we should set up a research station on one of the Martian moons.
Yes, I think a lot of us would love to set up a research station on one of those moons. I could totally get behind that.
The one that isn't going to crash into Mars.
Probably. Doesn't really matter.
John Seville is asking, wasn't there a small and ineffective demonstration outside the White House prior to the launch because it included nuclear power? For Cassini. There was, yes. You don't recall this? I do not remember. Yeah, so
I was in graduate school at the time.
So Cassini, like all of those spacecraft, had an RTG generator on it, and people were quite concerned when it launched that it was going to explode and scatter plutonium across the landscape. But that's not the only, and that one was like yes, rockets explode. That is a thing that happens. We agree. We can agree on that. And then also, but they then did another demonstration when the spacecraft did its flyby of Earth. because they thought that the spacecraft was going to crash into the Earth and spray its plutonium on the planet that time.
And what's kind of crazy is rocket fuel in general is not happy stuff. And so there's like this regular steady stream of, okay, it's coming through the atmosphere. Everyone watch out. It might have a little more stuff on it than we'd like. And so plutonium is really not the biggest concern out there all of the time.
Yeah, I mean, if you're concerned about radiation, you never want another coal plant to operate because there's more radioactivity coming into space from coal plants. But also, we know orbits. Like, there's no way it's going to crash into Earth, right? But
right.
Yeah.
Yeah, and random cool side note, one of the extra RTGs, radiothermal generators, that was built for Cassini ended up being ended up getting used for the first time because it was an extra, ended up getting used for New Horizons. So we had a power generator for New Horizons thanks to the Cassini mission.
Paul Gracie's asking, isn't the Martian moon gravity so low that one stumble could put one into orbit? All right, I'm going to have to do this math again. Hold on. The surface gravity, the escape velocity of Phobos.
And I still need to do that math. So I have a question for the audience, because some of you out there may know this. I've been trying to figure out a good way to do handwriting that I can get into my computer using OBS, other than sticking a camera over my shoulder or on my forehead or something, because that would look really stupid. So if anyone knows like how to do a homemade document camera so that I can handwrite in resolution easier than what you can do on an iPad to get the content into OBS, I want to know so that I can do these kinds of random calculations for you guys.
That's cool, and I can probably help you figure that out.
Okay.
Yeah, but we'll talk about this.
I got flummoxed earlier today.
Yeah, I mean, I still don't know how to let you be able to see what the show looks like. So
yeah, but if I'm running OBS on my side, I don't know how to do the handwriting part.
Yeah, I know. I think I can help you figure that out.
Okay.
Yeah,
that's what I need.
All right. So I did the math.
Okay.
And I got 11.39 meters per second, or 41 kilometers per hour, is the escape velocity of Phobos. In other words, if you can move 41 kilometers per hour, you will escape Phobos.
What was that in meters per second?
11.39.
Okay, so that's faster than your human can.
Yeah,
generally.
so I mean, we can, we walk at whatever, 6 kilometers per hour. A really fast runner can go 25, 30, 40, well, 40, pretty close, right?
I want to figure out what a jumping spider can do. This is the kind of random information, because like jumping spiders, they'll run your ass down. And so I'm betting some of them have the power to do something like this.
I'm just looking up the speed of a jumping spider right now. I'll let you know if I find it.
Okay.
Yeah, that's awesome. Jumping spiders are the best. We were doing an episode of Shooting the Guide to Space, and Carla's got on her camera this. You can hear me talking in the background, and then but the shot that she's got on her camera is this little jumping spider climbing up and down on the camera strap, and he was like turning around and looking at her. And then, moving up and down on the camera strap. That's what Carla tends to be looking for as we're shooting episodes out in the forest.
We have an orb spider that has decided that our kitchen door is the best place in the world to build a web. And it builds it at a height that I didn't notice this for a great period of time because I just walk right underneath the net every day. And when we had people out for the eclipse trip, two of our companions walked face first into this web multiple times, and my husband's done it multiple times, and the spider just sits there going, ha ha ha, I got humans, and it waves its arms at you. It's just a happy little orb spider.
One quick update. I finished reading We Are Legion, We Are Bob.
Isn't it fabulous?
I liked it. I'm going to have to read the rest. Like, I really enjoyed it, but it really felt to me like someone who is clearly a computer programmer in their regular life, or an engineer, working through a to-do list. So I'm still waiting for the story part, but the theme is great and the solutions are great and the humor is very the Martian-esque. It's very Andy Weir style humor. Have you read all three?
Yeah.
Yeah. Okay. All right. So I'm hoping that there is a larger, because this could just go on forever, right? Like the way this book just goes is like, and then we did this, and then we did that, and then we found that thing over here, and then we made some more of ourselves, and then anyway. So, but I'm really enjoying the writing style, and I'm really enjoying the concepts are lovely, and I really really like it. It's like finally somebody is sort of grappling with the kinds of things that I like to think about. So.
It's much more of a concept book than a plot-driven book.
Yeah, and so that's all. So that's what causes it to lose half a star in my mind. It's just that, right? Same with Three Body Problem, which is sort of, is another very challenging book with some great ideas, but anyway. So, but I give it my almost full thumbs up, and agree with you. Okay, so Bill Druin is saying, I wish there were more. We would clarify which Lagrange system we mean. I know that James Webb's L2 and the L3, you mean talking about space stations, are different systems, but it confuses noobs. Man,
sorry.
Lagrange points.
You always have to say two objects. So like.
Yeah, you can't say the moon Lagrange point. You have to say the Earth moon Lagrange point. The Earth Sun Lagrange point, or the Sun Earth Lagrange point.
Yeah.
Yeah. So, but it's that L1 through 3 are gravitationally unstable. L4 and L5 are gravitationally stable, as long as the object is a 1/25th. I looked this up. The mass of the smaller of the objects in the Lagrange relationship.
That is something I did not know, and that is cool random information to have in my head.
Yeah. So when the weight has, if you get any bigger than that, and it won't stay in the L4 L5 Lagrange point, it will drift out and crash into your object. Bill, did that clarify things for you? I mean, you probably deeply understand the Lagrange points, and that is just me making them more complicated for everybody else. All right. Let's see. Quailube's got a question. Quod libet. Concerning Titan, given there may be some internal heat source and possibly cryovolcanoes, would it be possible to witness such an eruption from orbit? Is it possible for the cryo smoke to get high enough to be detected from the orbit? So, like with Titan, you've got, tell me if I'm getting this wrong, right? Which is that with Titan, you've got, as I mentioned, it's a sandwich, right? It's like an ogre, right? It's got layers. So you've got this outer...
An ogre?
Sure.
Like
yeah.
rar?
Yeah.
Okay.
Yeah. Ogres are like onions. They have layers. So you got the outer shell. Don't worry, the chat's going to catch up with me in a second. The outer shell is this, ice with a methane hydro system, right? And then underneath that, you potentially got this liquid water underneath that. So the question is, we know that we can see on Titan, we can see the methane seas, but on Enceladus, we can see the geysers reaching space. So the question is, have we or can we see the geysers from Titan somehow getting out to space as well?
Probably not, because the atmosphere is so thick that the geyser would have to push through that atmosphere to then get further out. And with an atmosphere that thick, the amount of internal pressure that would be required, we haven't really seen evidence for that yet. So basically it has a blanket on it.
Right. So what you're saying then is, to really find this, we would need to send some kind of drilling spacecraft to the surface of Titan and its team of astronauts with their not spacesuits but warm coats to work this drill and to find potential hotspots where maybe the subsurface ocean is leaking out onto the surface of Titan and interacting with the methane.
So another way to do it is like what we did with Europa, and we used infrared imaging to look for hotspots. So with Europa, we were eventually able to figure out there's one area that seems to be warmer consistently that is associated with where we see geysers. I'd say it's probably way easier and less satisfying to use thermal imaging.
Okay, fine. But what?
I'm still trying to figure out how this is like an ogre.
Shrek, the movie Shrek.
Okay.
Yeah, if you watch the movie Shrek, he says he's telling the donkey that ogres are complex. They're like onions. They have layers, and he cracks open this onion in the donkey's face.
Okay.
Too obscure.
So
maybe.
not Lord of the Rings, which is where I went and got stuck. I was in Mordor, and you were in a happy little fairy tale forest.
Yeah, exactly.
Okay.
But the point is, okay, so fine, you found your hotspot. Then what?
So you found your hotspot, and then it's easier to justify to get funding to go down, but you have to do it one step at a time.
The drilling team down. That's all I'm saying. And I wouldn't send like oil drillers.
Bruce Willis?
Yeah, I wouldn't send Bruce Willis. I would send that team from Lake Vostok, the Russian drill team that got to the bottom of the ocean through the bottom of the glaciers in Antarctica. They are ice drillers. They know their stuff. It's an amazing accomplishment. Red and Sea Brazil, any news about those inflatable modules on the ISS?
No, but I haven't been watching, and that's the kind of thing where they don't necessarily have press releases every time they do sensor checks. So the fact that I haven't heard anything tells me that nothing has gone wrong. So I assume everything is proceeding nominally, and nominally is your goal in space flight.
It's not broken.
Yes.
All right. Well, I think it's time to wrap things up. We've reached the end of our hour. Thanks, everyone.
Okay. And hey, if you're a patron at a sufficient level, there are Patreon office hours in 12 minutes. We love getting donations via PayPal, but it's harder for us to communicate with you. So if you donate via Patreon, first of all, you get office hours with me roughly once a week. And it also is just like awesome in so many other regards for how we can communicate with you. So go help support us.
patreon.com/astronomycast.
And we're hoping to really grow the show this year and start doing some new things, planning more trips, planning more adventures, more science. And we can only do this with help from you. So go out and help us science.
Do you know what we're going to talk about next week?
Arecibo.
Right. Okay, cool. All right, I'm going to go back to bed. Good night, everybody.
Okay. Dream well.
I will. See you later.
Bye-bye.